In this video, I'm going to talk about the extreme value theorem. Let's say we have a function f that is continuous on some closed interval ab. So let's say ab is a closed interval. Then f attains a maximum and a minimum value in that interval. Then f attains a max and mean value in that interval in AB. What does this mean? That means that there is a point C which is an element of A comma B, right? Closed interval AB, such that f of C is the absolute maximum or global maximum on that interval. Absolute max or global max. And similarly, there is a point D in the closed interval AB such that f of D is the absolute / global mean or minimum. Now I'm going to try to show that to you. I am going to try to prove that to you. However, the proof is a little bit involved for this level. Okay, this is beginning calculus, so the proof is a little bit involved. So please be patient with me as I go along and watch the video a couple of times or multiple times if needed. To show this, to prove this statement, what I need to do, I need to prove something else. So that's something else. Let me start with is this. Let's say again f is a continuous function. F is continuous on some closed interval a comma b. Then f is bounded. Then f is bounded on that interval, on that closed interval. What does that mean? It means that if f is a continuous function on this closed interval, f is bounded above by some number, let's call it m. That means all the values of x within this interval, f of x is gonna be less than or equal to that m that's bounded above by this number uppercase m, and bounded below. When we say bounded, there is a little bit of tricky thing here. The tricky thing is that it could be bounded above or bounded below. So bounded below is going to be the case when there is a little m such that f of x is greater than or equal to little m for all values of x in this closed interval. That's what it means. So if f is continuous, then f is bounded on that closed interval. Continuous on a closed interval implies boundedness in a closed interval. So let's say we kind of prove it slightly differently by contradiction. So let's say f is not bounded, okay? F is not bounded, that means it could increase unlimitedly, meaning indefinitely it could increase. And similarly, we can prove the decreasing side going towards infinity, negative infinity. So let's say f is not bounded. Then what we can do, we can find an x sub n such that f of x sub n is greater than n. So we can find x sub n, which is, by the way, an element of a comma b. In this closed interval, we can find a point, some point x sub n such that f of x sub n is greater than the number n. N, by the way, here let me clarify, n is a natural number, or n is an element of n. Okay. Now this is true for all n. That means I could find x sub 1 such that f of x sub 1 is greater than 1. I could find x sub 2 such that f of x sub 2 is greater than 2. I could find x sub 3 such that f of x sub 3 is greater than 3. Why can I do that? Because my assumption is that the function is not bounded, right, in that interval. And in general, I could find x sub n such that f of x sub n is greater than n, and it keeps going. So in essence, what we have done is that we have created a sequence of numbers, x sub 1, x sub 2, x sub 3, dot dot dot, x sub n, dot dot dot, and it keeps going. And all of these numbers are, by the way, element of coming from the closed interval AB. So this is a sequence I created by picking numbers from this interval such that these conditions are satisfied for each of these x sub n. So that will show that the function is unbounded in the positive direction, right? Now, there is another theorem that I can have to use that I didn't talk about, or I'm not going to show the proof of. It's called Bolzano-Weierstrass theorem. So it's called Bolzano-Weierstrass, Weierstrass theorem. What this theorem says that if you have a bounded sequence of real numbers, okay, this is a bounded sequence of real numbers. Y is coming from this interval, closed interval AB. If you have a bounded sequence of real numbers, you can always find a subsequence. From this, you can find a subsequence such that it converges. Okay, you can find a subsequence such that it converges. So this sequence, in the realm of math, we denote it x sub n. N goes from 1 to infinity. That's what the notation is for, representing this sequence. So Bolzano-Weierstrass theorem says that since this sequence is bounded sequence of real numbers, we can always find another sequence, because this is infinitely many numbers. We can create another infinitely many numbers from this sequence, which is going to be a subsequence that is going to converge. Okay, so that is to say, we can find x sub n sub k. Okay, another sequence. K goes from 1 to infinity. Okay. So this n kind of tells you that it's coming from this sequence, and k is the subscript that's going to run it through 1 through infinity, such that this converges, right? Now, there is yet another thing you kind of have to think. For a closed set, okay, so this is a closed set of real numbers, okay, any sequence coming from closed set converges to a point in that set. So this sequence is coming from this guy, because the original sequence from which we derived, it also comes from here. So the subsequence must be coming from here. And this subsequence converges. But this is a closed set, A comma B. So it must converge to a point in A comma B. So let's say x sub n sub k converges to some point x. Let's say call x, which is an element of AB. All right. Now, if x sub n sub k converges to x, so f of x sub n sub k must converge to f of x, because we are dealing with a continuous function in this interval, in this closed interval. However, we know that f of x sub n sub k is greater than n sub k is greater than or equal to k. Why? Because this is coming from here. So f of x sub n sub k must be greater than or equal to n sub k, okay? N sub k is greater than or equal to k. So that means it tells you that the function diverges as the sequence approaches the value of x, which is, by the way, a contradiction. Why is it a contradiction? Because according to our assumption, the function is supposed to converge for the point x, which is within the closed interval. But since we assume that the function is not bounded above, and we assume that the function grows indefinitely, we find ourselves in a situation where it violates our assumption that the function is continuous. So therefore, we conclude that our assumption is wrong, which is that the function is unbounded. That means it grows indefinitely in the positive direction. So therefore, the function is bounded above. And with a similar argument, you can show that the function is bounded below. So we just showed that if a function is continuous on a closed interval, then it is bounded, meaning it is bounded above or bounded below. Now, this proof, if you understood it, it's great. However, if you did not, just take the conclusion. That's what I would say. A function continuous on closed interval is bounded above or bounded below. That means it does not grow indefinitely. That's what it says. Or it does not decrease indefinitely. Now we are ready to show or prove the extreme value theorem. Just to remind you what the extreme value theorem says again, f is a continuous function on closed interval AB, then f has global maximum and minimum in that interval. Okay, so that's what it is. So there are values c and d in this such that f of c is the global maximum and f of d is the global minimum. That's what we are trying to show. Now let's define a set. Let's call this set to be A, okay, such that so set A contains all the f of x or the y values, such that x is coming from closed interval. X is an element of A, comma B. That's what it is. Here, note that A is not an empty set. A has some elements. So this set A has elements in it. Now, the theorem we just proved that says that if f is continuous on a closed interval, then f is bounded. So this is the set of all the values that f could take on this closed interval, which is contained in this set A. So A must be bounded. So that's where we use the theorem we just proved. Let's start with the upper bound. So A has an upper bound, and of course A will have a lower bound as well because it's bounded. So if we can show it in one direction, the other direction can be shown similarly. So A is bounded above by some number. Let's call it M. So it must be the case that all the elements in here is less than or equal to M. And if it is bounded above, then here I have to use another theorem kind of. There is a least value among all the possible such M's, okay, which we call supremum, okay. So if this set has an upper bound, okay, among all the possible upper bounds, there is a least value. We call it supremum. Let's say M is the supremum of the set A. Okay, M is the supremum of this set A. So we claim, okay, so our claim is that there is a value C in this closed interval AB such that f of C is equal to M. That's what we want to show. Since M is the supremum, it is possible to take a natural number. So let's say n is an element of the natural numbers. Natural numbers are 1, 2, 3, 4. So just to remind you, 1, 2, 3, 4, etc. These are natural numbers. So we can find the following. So if M is the least highest value, okay, or the supremum, okay, if M is the supremum, it must be the case that M minus 1 over n is not a supremum anymore because it's less than M. So this must be less than M. So that says that there must be a value, let's call it x sub n. There must be a value x sub n in this closed interval AB such that f of x sub n is less than this and m minus 1 over n is less than that. So that means if m is the supremum, then m minus 1 over n is not a supremum. So we can find a value in between m minus 1 over n and m's, okay, such that that value will be f of xn and n will be coming, x sub n will be coming from there. So that's what it is saying. So that means we can create a sequence again. So we could find a sequence of numbers x1, x2, x3, dot, 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 xn, dot, dot, dot. Just to give you an example, m minus 1 is less than f of x1 is less than m. Then m minus 1 half is less than f of x2 less than m. M minus 1/3 is less than f of x3 less than m. And I can keep going. M minus 1 over n is less than f of xn is less than m. As you can see, as n gets bigger and bigger and bigger, what happens? The distance between m minus 1 over n and m is getting smaller and smaller and smaller. So that means in the limiting case, this f of xn in between has no choice but to converge to m. So this f of x sub n that we found, it must have to converge to m. Now, if this sequence is such a sequence that converges to a value, so if this sequence x sub n 1 to n converges to x in a comma b, then we are done. We found a point in x in this interval such that f of x is equal to m. However, these sequences are arbitrary sequences that we picked up, right? Arbitrary numbers. We constructed this sequence by picking arbitrary values from the interval a, b, right? So this sequence may not converge to a particular value, even though this relationship holds true, okay? So what do? Again, we use the theorem that we used towards the beginning of the proof, which is every bounded Bolzano-Weierstrass theorem. Bolzano-Weierstrass theorem tells you every bounded sequence of real numbers has a subsequence that converges. So I'm gonna have x. If this one converges, fine. If it doesn't, I'm gonna always find x sub n sub k such that it converges to a value of x, right? and that x must have to be in that interval a comma b, closed interval, because in a closed set, if you create any sequence, okay, out of that closed set, and the sequence must converge to a point in the closed set. So that if that is the route that we have to take, we still have found an x such that f of x is equal to m. Therefore, we just showed that for a continuous function, okay, for a continuous function on a closed interval, a maximum value takes place within the interval. So that means on the closed interval AB, we found a point x such that f of x is equal to m, the supremum. Now this x, I just gave it a name c, so that x is equal to c is equal to x, or x is equal to c, so that means f of c is equal to m. So that's the maximum value, and we found such a value in that interval, closed interval AB. Now, in exactly the same way, by considering the other side, infimum, what we call, instead of supremum, if my infimum is m, we could use similar argument and show that there is a value d in the interval a comma b such that f of d is the minimum value on this interval. This proves the extreme value theorem. This is a little bit involved, okay? So just to summarize, to prove the extreme value theorem, I have used some of the other theorems. So one is this: if f is continuous, on closed interval AB, then f is bounded, okay? I use this. And then also, if x sub n is a sequence of bounded real numbers, then there is a subsequence x sub n sub k that converges. I use these two results to show that the conclusions of extreme value theorem holds. And this proof is a little involved. So if you don't understand it the first time, it's okay. You may have to see the video or watch the video multiple times, and then it will start to make sense. I hope that this discussion was helpful and not too difficult, and that to the point you can handle it. Hopefully you will be able to handle it. Thank you very much.